All right, we are going to be starting a brand new chapter here today. We're in chapter 4, and we're going to be talking all about exponential functions and kind of what they look like. We'll get into logarithmic functions as well, and we'll talk about how to evaluate with these kinds of functions, how to graph them, and do all kinds of different stuff here. Okay, so for today, we're going to kind of give you an underlying idea of what exponential functions are, what they look like, and kind of just give you an idea of like where we get some of this information from. Okay, so we're going to go over how to evaluate exponential functions. We'll get into a little bit of graphing. We'll talk about something called e, which is a number that shows up in math. That's kind of a big deal when we're dealing with exponentials. Just like pi was a number that you maybe saw in geometry. That's kind of something that shows up a lot when we have specific shapes. So we'll kind of go over what E is. And then we'll also talk a little bit about some compound interest formulas and how to use those. The first thing we're going to go over is just how you would use an exponential function to evaluate an equation. So this first example kind of shows you what an exponential function is going to look like. If you look at this really quick, I'm just going to highlight this equation here in the problem. You might notice that the x isn't necessarily standing next to a number. It's in like an exponent spot. So what makes something an exponent, like an exponential function, is that the letter, the variable, is being used as an exponent. Okay, and so that's going to create some situations where an amount is growing or it's decreasing very, very quickly. So, for example, if you're talking about maybe like biologists or like chemists who are maybe looking at a specific maybe bacteria or something like in a petri dish, and they might be looking to see like how quickly it's growing. They might use an exponential function to display how fast or how rapidly the bacteria or like the germ is spreading. You also could deal with like something going down over time. So being able to kind of see these things in real life is when something starts to get really big really fast, or it starts to get really small really fast. And that's because we have this exponent as a variable. So you can see down below, this equation that they're giving me has that x up there in the exponent spot, okay? But it also is giving us some numbers. So let's see what these represent. So they're saying that this function models the average amount that is spent f of x in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at the shopping mall? So I just need to be able to decide what my x is, because that's what I'm going to be plugging into this equation. Now they're saying x represents hours up here in the description, and they're saying how much would be spent after 3 hours. So my x would be 3. And so I'm going to plug that into my formula here. So it's going to be 42.2 times 1.56, and all of that's going to be raised to the third power, okay? At this point, you're going to want to just use a calculator because you're not going to want to maybe even try to mess with those decimals, but I would just type this in. Now you could do the 1.56 to the third power first and then take it times 42.2. You're going to type all of that in and you're going to get 160.21. Now that's me rounding because I'm talking about money here. So I'm rounding up to 2 decimal places because that would be dollars and cents. So $160.21 would be what's estimated to be spent. And that's what they have down here too, okay? So they're saying that the average amount would be about $160 if they were maybe just rounding to a nearest dollar amount. All right, so let's look at another one here. This next one says that in 1986, the explosion at the Chernobyl nuclear power plant in the former Soviet Union sent about 1,000 kilograms of radioactive cesium-137 into the atmosphere. The function f of x equals 1,000 times 0.5 x all over 30 represents the amount of cesium remaining x years after 1986. If even 100 kilograms remains in the area, it's unsafe for humans. Will it be safe for humans in 2066? So that's 40 years from now, which would have been 80 years after the initial explosion. So what do you guys think your X is for this problem? Good, it'd be the 80 because X says that it's years after 1986. So 2066 would be 80 years after the initial explosion happened. So our X is going to be 80. And then we're going to plug this in. So 1,000 times 0.5, and then that's raised to the 80 over 30. Okay, so I'm going to give you a minute to go ahead and calculate that. Okay, so what did you guys get for an answer? If you round it, 157.5, okay? So the question asked, will it be safe for humans? So what did they say the threshold was? Yeah, and this would be kilograms, okay? So they said that if 100 kilograms remain, it's not safe. So we're still over that. So no, not safe for humans. All right, any questions on that? Okay, let's go ahead and turn the page here. And the next thing we're going to get into is how to graph an exponential function. So like I said, when you're dealing with an exponential, what that means is that your graph or your values that you're dealing with are going to be getting really big fast or really small fast, okay? So when we get these, you're going to start to see that your numbers start to get really, really big or really, really small. When you're dealing with graphing them, I would say you probably only need a couple of points, and then you should kind of know like the general behavior of a graph. But then I would just graph what you can. All right. So I'm not expecting you to be able to graph everything. Okay. All right. So I'm going to talk through how we would do this here with the table. So they want me to graph this equation, f of x equals 3 to the x power. Now, if you would like to, if you have one of my calculators, you can type this into your table and it'll give you all those values, okay? And that's probably what I would advise that you do, unless you want to take 3 and raise it to all these numbers individually. I think using a table is going to be a lot easier. So I'm just going to type in 3 to the x power into my table here, and then I'm going to go to values. Now, my table starts at -2, so I'm going to have it start at -2. And then I'm just going to look at these. Now, if you're getting fractions, like my y right away starts out as 1 over 9, you can arrow over. So just hit your right arrow over. And then that button right above the enter sign that's got the double arrows, if you tap on that, it'll convert it to a decimal down like on the bottom of the screen there by your table. So this is 0.1 repeating, but it might be best if we kind of think about it as a decimal, because we are going to have to graph this. Graphing fractions can be really hard if you're not sure exactly where it is. So I would maybe think about what is it as a decimal. Okay, so I'm going to write 0.1 repeating there, and then I'm going to keep going. So the next one is -1. It's at 1/3, which would be 0.3 repeating. 0 is at 1. What's 1 at? 3, and 2 is at 9. Good. All right. So let's go ahead and graph this here. So I'm just going to have to estimate to the best of my ability for some of those beginning numbers because they are really small. Okay. So I'm just going to kind of zoom in on this graph for a second so you can kind of see where I put those points at. Now, if I were to continue to look at these numbers that are going negative on the x, like on my table, if I go to like -3, -4, -5, if you just kind of arrow up, what does it appear is happening with our y values? They're getting really small, right? Like I'm all the way at negative 18 and it says point, there's like 9 or 10 zeros there and a 3. So it's really small. Do you think though that it's ever going to actually equal 0? It's not. Like you're going to get really close to 0, but it's never truly going to equal 0. Okay? So on here, when you graph this, this graph is not actually ever going to cross the x-axis. So how I like to draw that is I just draw like an arrow that kind of rides up really close to the x-axis, but it's not going to cross it. So it's going to look something like that. Okay, now do you remember what it's called if a graph can't cross a certain region or area? We had a special name for that when we were dealing with our rational functions last chapter. Yeah, it's called an asymptote, okay, or asymptote is maybe how some other people would pronounce that. But so that x-axis would be when y equals 0, and it's not going to hit that point. So my asymptote here would be at y equals 0 because it's not going to cross that point. That's kind of like a boundary that we have for this exponential equation. Now let's talk about domain and range. So domain would be all of your x values. It looks like I could put in any number I want for x. Like I had some negatives and some positives. I even had 0 here. So it doesn't appear to be any restrictions on my x values. So I'm going to go ahead and just say negative infinity to positive infinity would work. But my range, okay, we can't see anything smaller than a little bit above 0 here. So I'm never going to have a y value of 0. But it looks like I'd have as big of numbers as I want. So even if I go back to my table and I start to go down to the positives, because we only went to 2, but if I went up to like even like 10, is at 59,049. I mean, that's really big. There's no way I'm graphing that, right? So, but it continues to get bigger and bigger and bigger. So we would represent that with positive infinity. All right, so now that you kind of have an idea of how this graph is going to work, okay, as I was saying, so now that we kind of know what a general form of these exponential equations looks like, now we're going to start looking at what happens if I start to like put in some other numbers into the equation. So like 3 to the x power, I wouldn't say it's like the true parent function, but it's pretty close to like what we would maybe call the parent function, okay? Remember, a parent function is like what it started out as originally when we didn't do anything to it to make it look different or move it around on the graph at all, okay? Now, when we start to add numbers to the exponent, or we start to add numbers after the 3 to the x power, that is going to start to impact the way that the graph looks. So I'm going to go over in this next example, we're still using kind of this as like our baseline for where the original graph was, but we're going to talk now about if we have these transformations, what does that start to do to our graph, okay? So if you need to, you can always regraph your parent function on here just so you can kind of see like where it is originally. Since we just graphed it up above, I'm probably not going to put the parent function on this graph, but I am going to start to ask myself like what's happening here with these transformations. So the first one I have says f of x is equal to this 3x, and then up in that exponent, it's got minus 1, okay? So anytime that we have a number that's impacting the exponent, that is going to make it go left or right. Now remember, with left or right movement, we have to think backwards, okay? So I know it says minus 1, but really you put in a positive number there because it would always be minus to begin with. So if it was minus 1, what movement happened here? Yeah, it's going to go right 1. So I'm just going to write here, this is going to make the graph go right 1, okay? So on my parent graph up above, I'm going to take all those original points that I had, and I'm just going to shift them all 1 to the right. So starting at like 2, 9, just because those are the easy points to graph since they're whole numbers, I'm not going to go to 2, 9 again. I'm going to start at 2, 9, but then I'm going to just go 1 over to the right. So it's actually at 3, 9 now, and I'm going to draw a new point. Okay, same thing would happen at 1, 3. I'm going to go up to 1, 3, and I'm going to go 1 to the right, so now I'm at 2, 3. And then I'm going to keep doing that for the rest of my points here. So the next one I have was at 0, 1, so I'm just going to go right 1. And then those next ones would start to get really close to 0, but you can kind of see how this whole graph just shifted right 1. Now when I draw this in, it's still not going to cross the x-axis. So let's keep that in mind as we answer the questions over here about domain and range. So it still does not have any impact on my x values. My x's are still going to be negative infinity to positive infinity, so that's still my domain. But my range values are going to start to increase, okay? But they're still not going to ever be 0 for my y's. So my range is still going to be 0, positive infinity. All right, now the next one's a little bit different. This one is saying 3x plus 4, but this time the 4 is on the outside of the exponent. It's not up with the x anymore. So this is going to cause it to go up or down. If it's plus 4, what direction do you guys think it went? Good, this means it goes up 4. Okay, so I'm thinking back to my original points. I had that one at 2, 9 to begin with, but now I got to go up 1, 2, 3, 4. So now I'm at 2, 13. My point that started out at 1, 3, I go up 1, 2, 3, 4. And then 0, 1, you go up 3. So I'm at 0, 4 now. And then I know that these ones are going to get really small, but they're not going to cross this new boundary line, okay? So I'm going to, oh, I don't think I went up far enough. Hold on a second. Nope, I did not. I graphed this part wrong. This one should have been at 5, and then these ones should be getting really close to 4, but they're never going to cross 4. Okay, so x values are still not impacted by this at all. So my domain is still negative infinity to positive infinity. Okay, now my range is going to change slightly here. Because it moved up 4, it's going to move that asymptote up 4 as well. So originally the asymptote was at y equals 0, okay? But now that it moved up 4, it's going to never equal 4. Like you're going to get numbers that are really, really close to 4, but it's never going to be actually 4. So for my range, I have to just reflect that and say 4 to infinity is my new y values. Those are my new restrictions here. So for this last one, what movements are happening here? Good, it's going right 1 and up 4. So it's kind of taking what we just talked about and it's combining them together. So I'm going to start back at 2, 9, because that was my original point. I'm going to go right 1 and I'm going to go up 1, 2, 3, 4. The other thing you could do, guys, is that green line that I had, that one that we just graphed, you can move all of those right 1 to just make that reflection there. They're going to overlap a little bit. You're going to have some overlapping of the lines here. So it looks pretty similar. It's just everything got moved right 4. Okay. So, whoops. What's my domain? Yeah, it's still negative infinity to positive infinity. And what's my range? Good. Still 4 infinity. Okay. Questions on any of those transformations? Okay, before we move too far away from this, I just want to add something to the bottom of the page here. I'm going to kind of summarize some of that information about transformations. So there's different ways that it can be impacted. You know, we saw up above that it can go left, right, up, down, but there are some other things that can happen to your equation that will cause it to act a little bit differently. So I'm just going to summarize that all down here. The first thing I want you to just be aware of is we'll kind of go over the up and down stuff first. So I'm just going to make like a box down here. I'm going to kind of divide this into 4 sections. Okay, So for the first one, if you have your term or your piece that's raised to the exponent, so like I'm just going to say b to the x is like the original form. If there's a minus c added to it, that is going to cause it to go down. And so if the same exponential equation is adding a number to the end, that's going to cause it to go up, okay? If the number that's being added is in the exponent, so if we have things that look like this, where b is raised to a power and it's x minus c or x plus c, if it's minus, we talked about how that's going to cause it to go right. If it's plus, that's going to cause it to go left. Okay, we talked about those. Now, these next ones are the ones that maybe we haven't seen yet, but you might see going forward, so I just want to make sure we cover them. The first one would be if there's a sign change sitting in front of the function. So like if it was a -3 to the x power, this is going to cause a reflection. And I'm going to use little r for reflection. That's from your geometry days, over the x-axis. If the exponent becomes negative, that causes a reflection over the y-axis. Okay. The other thing that we haven't seen yet is when there's like a whole number added in front of the piece that's got the exponent. So if you take a number times something raised to the exponent and it's positive, this is going to be a vertical, stretch, or compress. If it looks like this, where you have the number being in front of the x, so like something times the x, this is going to be a horizontal, stretch, or compress. That should summarize all of the changes that you could possibly see happen in a graph, but there might be times where more than one of these things is happening. Like maybe there's a reflection happening and something is being shifted to the left or to the right or up or down, okay? So they can combine some of these things as well, just like we saw in that last example that it moved right and it moved up. So they might kind of throw some of those things in there together, okay? All right, so with the problem that we've seen so far, it's been like a whole number raised to an exponent, like we had 3 to the x. If I had something that said like 4 to the x or 5 to the x power, they would all look like this. This is called an exponential growth equation because as you go along the graph from the left side to the right side, the graph is going up over time, okay? So what I mean is as I read this graph going from left to right, it's going up. So that's exponential growth. Now, sometimes we can have exponential decay, or that would be when it's like decreasing over time. So let's talk about what that looks like. So if you turn your page over to the next side here, if you see a fraction being raised to an exponent, this is going to cause your graph to switch directions, and this is going to become exponential decay. It's going to get smaller over time. So I'm going to create a table here. They didn't give us one, but we can just go ahead and add one here into the space. And we're going to do it to this equation. I'm going to use f of x just to keep it with what they have. And it's 1 over 2 now raised to the x power. Just like before, let's go ahead and go from like -2 to +2. And let's use our table to help us do this. So go ahead and hit your table on your calculator here, and let's type in this new equation. So we've got 1/2 raised to the x power, and we're going to start it at -2. Okay, at -2, what number do you have for your y? Good, a 4. What do you have for -1? 2, and then 0 is 1, and then what starts to happen? They start to get small, right? A half, which would be 0.5, and a fourth, which would be 0.25. And then they continue to go down, right? If we keep going down on our chart, we're getting smaller and smaller and smaller numbers. Again, they're going to get really close to 0, but they're never actually going to approach 0. So this is still going to have that asymptote at y equals 0 here. Okay, if we kind of go over here and sketch our graph, so we start at -2 up at 4. Negative 1 is at 2. 0, 1. 1 is at a half. I'm going to zoom in here. It gets so small. And then 2 is at a quarter. So you can kind of see how on this one, it's going to go down over time. But again, it's going to ride right next to that x-axis because of that asymptote. And that's why we said the asymptote there would be y equals 0. Okay, what would still be your domain though? Yeah, it's still negative infinity to positive infinity. And then what would be the range? Think about your y's this time. So the lowest is still 0, right? So we aren't ever going to equal 0, but we have anything above 0 showing up on our graph because everything's staying positive on the y side. So I would still say 0, comma, infinity. I think sometimes that can look a little backwards to us when we think about the graph because I think you're thinking about how it started up at infinity and then it went down to 0. But remember, when we're writing it out in notation form like this, we're starting from the smallest values it could be up to the greatest values it could be. So that's why 0 comes first. All right, so that's really the only difference between what we were just doing and this one here is that the graph switches its direction a little bit. Now, let's talk about what happens when we start to do some transformations. Okay, so we're still using this as like our parent graph. What would be happening down here on this first one? What is this plus 2 going to make it do? Yeah, it's going to make it go left 2. So all those points that I had earlier, like negative 2, 4, that's going to go left 2. So now I'm at negative 4, 4. And then negative 1, 2 is going to go to negative 3, 2. And it's going to keep doing that. Okay, is my, whoops, I wrote the wrong thing here. This should have just been up above. Left 2. Did my domain at all change? No, still negative to positive. How about my range? Good, no change there either, 0 to positive. Okay, what happens on the second one? Yeah, the minus 3 causes this to go down 3. Okay, so my parent graph, that first point was at negative 2, 4. That's going to go down 1, 2, 3. It's going to start there actually. And then negative 1, 2 is going to go down 1, 2, 3, 4. Next point was at 0, 1. That's going to go down 1, 2, 3, 4. And that's going to keep going down this way. Hold on, I got to back up here. I think I graphed wrong. Let me zoom in. Yes, I did graph wrong. I think I went down too far on one of my points. It should look like this. Okay. What's my domain for the blue line? Good, still negative to positive infinity. How about my range? What is changing here? Yeah, we don't seem to go below negative 3 this time. So negative 3 is my new kind of restriction. That's my new asymptote. So I'm going to just go ahead and say y equals negative 3 is that new boundary line. All right, very good. Okay. So this just kind of summarizes what we just talked about. If your number that you're raising to an exponent is greater than 1, it's going to be an exponential growth. If it's less than 1 or it's in between 0 and 1, so you're dealing with like a half, a third, a fifth, maybe even something like 0.8, 0.75, those kind of things. If those are raised to a power, that's going to start it to become a decay function. Any questions on kind of the general idea behind exponential growth and decay.